Right, people. For the remainder of the session, maybe that will carry through a little bit in the next week, is range of three-phase problems to include three-phase balanced delta, which is a bit of a revision we touched on at last week. Three-phase balanced star and neutral. Again, we looked at that last week, but what we're going to do is do some problems we can see to switch on our meters, we can see the line current and phase currents are, and confirm that our calculations are actually get. Okay, and then taking that further, we're going to look at three-phase star and neutral when it becomes unbalanced, three-phased balanced delta with loss of line fault. We down so that I don't have to go from a star connected system to a delta one and back to star again, because the more times I connect it and disconnect it, the more likely I am to connect it up wrong. Alright, so we may well do that. We'll do this first delta one, then I'll switch to star, and I'll do all the star ones and then finish off the last delta one. Alright, so that's what we're going to do, using resistor values. And okay, so put you to work now. That'll help for me perhaps. Three resistive loads of 1950 ohms are connected in delta to a three-phase generator with a line voltage 300 volt. I'm going to change on here the voltages to 2. The line voltage we're going to use now is 2 volts. I noticed after I writ 300 last year that it says maximum 250 volts on it. But we'll keep to the rules and regulations. Alright? So 200 volt line, 1950 ohms, connected in delta. If we need it, frequency is obviously, it's coming off the main, so it's 50 hertz. So where would we start with that? How would you start with that? So if you're asked to sketch or draw the system, delta system, in an exam question, then that's what I'm expecting to see. May in some cases expect to see the 3 connections of the generator at the other end as well. Depends on what the overall flavour of the question is. Yep. What can we find from the information given? In which current? One big phase current. What does it equal? Sorry? Yeah, but we ain't got the line current, Christian.
Oh.
Yeah. You're right, but EL over R. All the R's are equal, so yeah. So 200 over 1950. Bit more than that. 3 more figures than that. Yeah. 103 or 102 milliamps then. 103 rounded properly. .013, which is 103 milliamps. Yep. So now we know the phase current. What else can we find? Well, is the line current bigger or smaller than the phase current? Yeah, because it's got some current from going from 2 directions. So it must be √3 times IP. .178 milliamps. 3 significant figures. Yep, so that one was I, that bit was B, and then C said the total power dissipated by the load. How can we go about doing that? If we look at one of them, we know that the total power is that power plus that power plus that power. So if we find one of them and then multiply by 3, yeah? So we can use IP so that for each phase, phase power is equal to I phase squared times R. So it's 0.103. We've got to go proper now. We can't use milli, and square that times 1950. .7 units, Mike. Watts. Yeah. Therefore, total power equals 3 times 20.7. 62.1. Watts. We had wire ones, I expect, in there somewhere. I don't know. They're inside a box, so you can't get your hands on them. Both for the fact. Right, the next one I'm going to leave you to have a go at while I disconnect the system and reconnect it in star. Okay, but we're going to have the same 3 resistive heaters connected in star to a 3-phase and neutral generator. So we're going to have a neutral line, but the line voltage is still 200 volts. Okay, so with those resistors reconnected in start with a neutral, calculate the new current flowing in each load, the new total power generated, and the current flowing in the neutral conductor. Alright? Remembering that when we add those currents together at the end, we must add the complex values, including the angle. So you'll have one current, all three currents will be the same, but one will have an angle of 0, the other one plus 120 degrees, and the other one minus 120 degrees. Alright? And what you should do from that calculation is prove that how much current flows in the neutral? None with a balanced load. Yeah? So that's the system. Line voltage 200 volts, 3 equal resistances, 1950. And we've got 3 separate phase voltages this time instead of 3 separate phase currents. Yep. So how have you started? What have you done? 3? EL? Yeah. Well, you got EL, you mean E phase. Yeah, what is it? EL of a root 3 is 115.5 volts. So you say. We'll see in a minute, won't we? Alright, next. Yeah. $59 milliamps. We'll see. All right. Next. Well, confidence should come from you all having the same result and all agreeing that that's the right result. Yeah? Yeah, either like that you're either all right or you're all wrong. Okay? Next, that's it for part A, yeah? Next bit. Power.
S equals 3 times E times IL.
Yeah. Okay. So you're doing P for each phase is equal to EP times IL. So that's 115.5 times 0.059, which is we'll see. Now I can't measure the total, but the total is what? 20.4. You could have done, well, yeah, but if you all done it differently and all got the same figures, they're all methods, aren't they? Because what could you have done? You could have done IL squared R. You could have done E phase squared over R. Formulas of power. reason S don't come into this, James, is because there's no reactive components. So you're not wrong in a way, because S and P are equal to each other in this case. Alright? Yeah? Alright, so whichever way you did it, hopefully you're right with 6.8 or so watts per phase. Yeah? Make it a total of 20.4. And then the last bit, did you prove that there's zero current flowing in the neutral, theoretically? C, IN is equal to, I'm going to use R, Y and B for red, yellow and blue, should be the three currents added together. They're all equal, but they've each got a different phase angle. So according to your figures, we've got 59 milliamps per phase. So that's 59 milliamps angle 0 degrees, 59 milliamps angle 120 degrees, 59 milliamps angle minus 120. Presumably you converted all them to a rectangular. So what are the results of that? No, if you do, well, if you do plus 120 and plus 140 or minus both of them, it doesn't matter. Okay, I think it's neater and more understandable as with one is at 120 and one's minus 120, but it's just a matter of opinion. Still get the same results. Yeah. So the effect of that one must be 59 plus 0, J, mustn't it?
Yes.
Yeah. The other two are? Minus. Is that this one?
Yes.
Minus 0.3 sig figures. So they'll be milliamps. Yeah, if you do 59, that'll be in milliamps. Millis.
So it's 29.5 minus 29.5.
Minus 29.5. 0.05 J. Yeah, yeah. Yeah. Those cancel out to 0 J, and those cancel out 0 amps. 0, sorry, ain't amps there. 0 plus 0 J amps. No current flowing in the neutral. Yep. Three-phase star plus neutral, unbalanced load. So the load from the previous problem has now changed, so that the load is unbalanced as follows. Phase 1, we'll call that the one that's pointing upwards. Keep the 1950 ohm resistor in it. Okay, we'll say that's the one with 0 phase angle as well, in terms of voltage. Yeah. On phase 2, the yellow phase, 950 ohms, and on phase 3, 3770 ohms. They're still connected in star with a neutral at a line voltage of 200 volts. Determine the new current flowing in each load. Okay. I'm not going to promise to keep changing meters around to measure all three currents. I'll see how easy it is for me to do that. Okay. And the new current flowing in a neutral conductor. Alright? So no powers in this. We're just interested in how that changes the currents in the system. And particularly the current in the neutral. is equal to 200 over root 3 divided, which is your 115 and a half. Yeah. Angle 0 degrees, so I put this in there, divided by the 1950, and I got 59.2 milliamps, angle 0 degrees, and that's the same result as we got with the other system anyway. Yeah. Current in the yellow phase, again 200 over root 3, angle 120 degrees over the 950 resistor I put on there, and I got a current of 122 milliamps, angle 120 degrees. So have you got currents of 120 odd milliamps? Yeah. Your angle might be different, but at least the 950 ohm one, you've got a current of 122 milliamps. And then IB, 200 over root 3, angle 0 degrees, that's angle minus 120, or if you like, minus 240. Don't do plus 120 and minus 240 though, will you? Because they're the same thing. Yeah. And that was over the 3770, and I got 30.6 milliamps, angle minus 120 degrees. So there are three currents that we should see on the three phases, according to the three resistors we've got connected. Yeah. And then B, IN, is equal to IA plus IB plus IC. Yeah. So we need to go, IR was 59.2, angle 0 degrees. That converts to, I got 8.8 plus 0J milliamps. IY, 122 milliamps, angle 120 degrees. That converts to minus 61 plus 106J. Does that figure look familiar? Oh, 50, yeah, I can see why. That's my old result from... No, I know where it is. That's my result when I had the voltage at 300. So that kind of crossed out and I picked it up somehow. Alright, 59.2. And then the last one, IB, I've got 30.6 milliamps, angle minus 120, and that converts to minus 15.3 minus 26.5 J milliamps. When I add all those up, I end up with minus 17.1 plus 79. Am I? Yeah. Plus 79.5 J. Well, 106 take away 26, make it. It just depends on how your angles is. When I convert that back to polar, I get 121 milliamps angle 102 degrees.
That's really confusing.
Yeah, but
The bit we got the same milliamps.
the angle, listen, the angle will depend on which load you put at what angle. So if you haven't put, because the angle of resultant will depend on where you've put them in. $19.50 on 0, is that what you've got?
Yeah.
I've got my $9.50 on plus 120.
Yeah.
No? Who has?
Yeah.
Yeah?
Well, mine's mine. Leave it again. That'd be why?
Yeah,
Because I'm doing mine at 0, minus 120, minus 240. Yeah, Christian on his is 0, 120, minus 120. I think the middle one is the opposite. That's the angle factor.
Yes. If you've done them a slightly different way round, the angle at the end are different.
Yeah.
What we're interested in here is that it causes a current to flow. Maybe I've converted it. What? Other than that's 81.
I got 80, yeah, I got 82 milliamps.